am the instructor named John.
I am the instructor named Dave.
Neither of us is bald.
And both of us are not wrinkling the clothes in your closet.
No, neither of us is wrinkling the clothes in your closet. Okay, so we're both going to talk about the words the, both, and neither today. The is one of the most frequently used words in the English language. In fact, I just used that twice in that one sentence. But even though these words are very familiar, their properties are subtle and a matter of some debate.
In fact, depending on your philosophical or linguistic opinions on this debate, you may or may not be able to represent these words using the first-order quantifiers. We're going to present two analyses of the meanings of these words, focusing on the word the. If you accept one of them, the one due to the philosopher Bertrand Russell, then you'll agree that the meaning of these words can be expressed in FOL. But if you prefer another, due to P.F. Strawson, then you'll see that there is no way to model these expressions in FOL.
So the issue is illustrated by one of those bizarre sentences that you by now are used to seeing in this class. So consider this sentence. The elephant in my closet is not wrinkling my clothes. Now, fortunately, there is not an elephant in my closet at the present time. So the issue is whether we should consider this sentence to be true or false, or whether there's something wrong with this sentence that makes it neither true nor false at the current time. If you think that this sentence is false, then presumably its negation is true, and its negation presumably says that the elephant in my closet is wrinkling my clothes, and that doesn't seem right either.
Similar issues arise with the words both and neither. What are we to make of these sentences? Neither elephant in my closet is wrinkling my clothes. Both elephants in my closet are wrinkling my clothes. In situations in which there are no elephants in my closet, or in situations in which there are 7 elephants in my closet. I have a very big closet.
So we're going to focus our attention on the word the and noun phrases of the form the a. These are called definite descriptions. Early in the 20th century, the philosopher Bertrand Russell proposed that sentences of the form the a is b should be analyzed as saying two things. The first is that there's a unique object with the property a, and the second, that this object also has the property b. This idea has come to be known as the Russellian analysis of definite descriptions, which is a logical but unimaginative name for it.
So according to Russell, the sentence, the elephant in my closet is wrinkling my clothes, should be true only if there is exactly one elephant in my closet, and if that elephant is wrinkling my clothes. Conversely, it's false if there are no elephants in my closet, 2 elephants in my closet, 17 elephants in my closet, whether or not they're wrinkling my clothes. It's also false if there is exactly one elephant in my closet, but it's not wrinkling my clothes. But that's a less interesting situation, except perhaps to my dry cleaner.
Okay, now we saw in a recent video that it's possible to express uniqueness claims using regular first-order logic quantifiers. So here's how we express there's a unique cube using a first-order sentence. There is an x, such that x is a cube, and for any y, if y is a cube, then y is equal to x. So now remember, the trick is to read this as saying that there's a cube, and every cube is identical to that very cube, represented by the variable x in this sentence.
So it's a pretty small step to follow Russell to translate this sentence, the cube is small, into FOL. We simply say that there is a unique cube and that it's small. So we end up with the sentence, there exists an x, such that x is a cube, all cubes are equal to that object, and that object is small. So if you agree with Russell that a sentence of the form the a is b asserts the existence of a unique object with property a, and this unique object also has the property b, then this is the translation into FOL.
Now, Russell didn't explicitly consider the words both and neither, but there's a natural extension of this kind of analysis to those cases. So, to say that both cubes are small is to say that there are exactly 2 cubes and that they, all of them, are small. The quantified expression ranging over all cubes speaks only about these 2 objects because there's only those 2 cubes. That's the only cubes that there are. So here's how we would say that. There are exactly 2 cubes, and every cube is small. Now, in our official language, the translation looks like it is a bit more complicated, and it's more obviously a generalization of the Russellian case for the single unique object. So there is an x and a y, such that x is a cube and y is a cube, and x and y are different. And for any z, if z is a cube, then it's got to be equal to one of those two, and both x and y are small. So that's how we would say it if we were writing it in the official language. So to translate the sentence, neither cube is small, we again analyze the sentence as saying that there are exactly two cubes. But in this case, we're saying that both of them are not small. So here we have, there are exactly two cubes, and for all x, if x is a cube, it's not small.
So according to Russell, here are the general translations of these forms of sentences. Sentences of the form the A is B is translated as there's an x that has the property A, all objects that have the property A are equal to that x, and that x has the property B. That's the first sentence here is the official language translation. The second sentence here is the translation into our informal language with these extended quantifiers. It just says there is a unique object such that A and all A's have the property B. On Russell's analysis, both A's are B is translated as there are exactly two objects with the property A and all of them have the property B. And the sentence neither A is B has the translation there are exactly two objects having the property A and all of them do not have the property B.